Hey guys, I'm just gonna wait for everybody else to show up. Yeah, let's give it just another little bit for other people. I just want to point out to if you guys are everybody is able to see things like the the videos up online on the Canvas page. I've been able to post our video links up onto our Canvas page. I'm also posting them to my YouTube page too. If you guys find it easier to watch it from there, it's totally fine. And then we'll spend some time today. I want to finish up chapter 1.3, going through that, and then I'll go back over my classwork. Okay, I've got classwork for 1.1 and 1.2, which is what our quiz is going to be based on tomorrow. So go back over to my classwork and start working through my classwork problems on our screen here so you guys can start to see that, see what that looks like. And then what I can do is before our quiz tomorrow, so like after class tomorrow, but before our quiz, I'll post the classwork solutions so that you guys can get a feeling for what those things look like if you didn't see me work it through on the screen already. And then the quiz tomorrow, we will actually have our class tomorrow, okay? And then the quiz will be an availability window, or I'm going to set it to be available from noon tomorrow until noon on Friday. You can start it at any time within that makes sense for you, because this is to accommodate different time zones that people might be in. But then once you start it, you have a limited amount of time in which to finish it. And then you'll need to upload your answers onto the like the department says we'll have 30 minutes to take the quiz, and then we'll have 45, then we'll have an additional 15 minutes for you to take pictures of it, scan it into PDF format, and then upload that to the Canvas page so that we can I can actually see it. And then we'll see how Canvas handles it from there. This is my first semester using Canvas. Under Blackboard, I used to be able to grade it actually online, and then you know, you guys can see my feedback. So we'll see how things go with Canvas. Okay, so with that said, let's do this. I want to finish up chapter 1.3, and then I'll go back over and start working through the classwork for the different chapter 1.1, 1.2. You guys, I encourage you to stay online and work through those classwork pages too. Those classwork things, you can download them. They're all on our Canvas page, some for week 1, some for week 2. You know, for the different chapter sections that we're working on. So I encourage you to please, you know, take a look at those. I also have office hours today at 1 o'clock if you want to stop by and ask questions. Okay, let's go ahead and get started. So this is chapter 1.3. We're going to continue. Let's see if I get this focused. I didn't focus this again, but that there, maybe the camera couldn't see very well. All right, so chapter 1.3. So this was our dot product. We started it on Monday. Okay, so what I want to finish up with today is an application of the dot product, like actually how we use it. Use it a lot in what's called a projection. Now, I have to warn you, a projection, it's a whole function. We're going to go over in detail what it is and how we actually make it work. You've probably seen part of it maybe in some of the physics classes that you might have taken, whether it's in high school or in college. Projections are something that you are going to use quite a bit in this class. We're going to actually do it out a lot. Your class notes for chapter 1.3, contain a really nice derivation for the projection, which I'm not going to go into because it's really nicely done out in your published class notes. So I encourage you to go ahead and do that. I just want to give you some background information and kind of like how do you picture it in your mind. So one of the things you want to be able to think about is, like, remember in physics when we talk about like forces, right? So say I've got some kind of like a rod, say for example, right? And I'm exerting some kind of a force on it, but I don't exert the force directly. I'm not going to push directly on it, but the force is like, maybe it comes on an angle itself. So this here is our force, right? So we've got some kind of force that's being projected, that's being pushed onto this rod. Okay, and I want to be able to think about like what's the how big is that force, like what's actually happening, but I have to break it up because the force is being pushed onto that rod at some angle, okay, to that rod. It's not going on directly. So you can think about this here as the magnitude of our force, right? So there's a couple things that we that we want to take a look at. This here, right? If I think about this part here, this is what we would call the force on the rod, right? This portion of it, okay? And this is actually the projection of the force, the big force, onto the rod. We're going to actually go through the whole math on it. So this is just kind of to get you to think about it. This portion of it here, right there, is the projection of this force onto the rod itself, okay? This portion here, let's say this is our actual force right there. This part, this is our actual force. This portion here, right? So where my force ends. So you can kind of imagine, right? This is my magnitude of my force. My force comes down to the rod at this point. This part right here is the projection of the force onto the rod. If I were to take this and I were to go right over to my, what would be like my y-axis, this is, I'm going to call F sub n, or I'm going to write F sub n is the force that's normal or orthogonal or perpendicular. These are all synonymous, perpendicular force to force on the rod. Okay, so there are multiple components that we have here. Say I've got my force, which is on some angle. I want to exert that. I'm going to project that onto my rod. Okay, then I've got this portion here that's at a right angle. Okay, it's orthogonal, it's normal to the force that's being put onto the rod. Okay, so how we would say this, let's see, I'm going to think about how I want to, this is just to kind of get you to think about what we want to do. So when we talk about a projection, okay, this is maybe how you have done it already in terms of like physics. You maybe have already thought about it already, right? So I would take the x component, it's going to be our cosine, right? It's going to be the force times our cosine. But let's talk about our projection, okay? So the projection, we would say, how we write this is, let me write it out like this. Our notes call it like this. We've also seen it written out like this. And I'll write it out into words. What does this mean? This is the projection of our vector v onto the vector u. Okay, this is how we read it. So projection of v onto u, projection of v onto u. So that little, what's in that subscript right down here is what's being projected onto. Okay, and I've got this vector v, so I'm going to draw it out like, draw it out more like this. So I've got this vector u down here. I've got, and I can do this in multiple ways. I'll show you multiple. So this is my v. Let's do it where we have u, and then let's say v looks bigger than that. So what is that projection going to look like? So v, when I project v onto u, this portion, I'll draw it in red. This portion here is our projection of v onto u. Okay, projection v onto u. Okay. It's a scalar multiple. I can also, if v is bigger, my projection could be bigger than my u. So this whole portion here, again, this is the projection of v onto u. Oops. Okay. Now we also have an orthogonal, our perpendicular component to our projection. So I'm going to draw this up here. this. Okay, this part here, I'm going to call Q. Okay, this Q, I'm writing out what these words are, and then I'm going to give you the math. So Q, V, is the, let's see, the orthogonal to the projection of V onto U. And orthogonal comes into handy too. So let's see this part right here. U, right there. Okay, so that's the same, right? So this is what it looks like when, you know, U is bigger, right? So this is a projection is a scalar multiple of V. Write that down too. Is a scalar multiple of our vector U. Okay, well, we're going to go through the whole math on here too so that you can see it. Okay, so now how I want to be writing this, right? I'm going to say, my projection of V onto U looks like this. Okay, I'm going to say it's V dot product with U divided by U dot product with U times U. Okay, I'm going to put this in a red box because this is actually our formula. I'm not deriving it here because it's really, there's a really nice, well done out derivation in our class notes. So I'm going to not do that here up on the screen because I'm going to afford you, if you want to see the derivation, you can go take a look in our class notes. But I take V is what I'm projecting onto U. So V dot U divided by U dot U. Remember with our dot product, we take in two vectors and we get a scalar. So I get a scalar divided by a scalar, and then I multiply that by my vector that I'm trying to project onto. That's why I say the projection is a scalar multiple of U. This whole value here is a scalar, and I'm multiplying it by the vector U. Okay. Now, our Q portion, remember our Q, so the by vector addition, right? Remember a vector addition. If I do Q plus the projection, I'm going to get my V. So if I go Q plus the projection, I'm going to get V. That's, I remember back at the very first day, I said, you know, our vector addition, right? I've got this vector here and a vector here. I make this parallelogram. The diagonal, right, is their addition, okay? So V is the addition of these two vectors right there. I can then subtract the projection to get my orthogonal component. V minus the V onto U. And I'll put that in green. We don't use this one as much, the orthogonal component to it, but it is something that you might have. The projection is what we're going to be using a lot. We use it a lot when we do, like, we're going to talk about like reflections and stuff later on, like in chapter 2 and stuff. So this projection comes into handy quite a bit. But like I say, I'm just giving it to you as a function, as a formula, and then the whole nice derivation for where this whole thing comes from is in our class notes. So I'm going to forward you there just so we can spend some time actually just practicing. Okay, so that's the projection formula. I'm going to pull out my example, my lecture examples. Okay, so this is chapter 1.3, lecture examples. I'm going to do example 3, which is actually calculating a projection. Let's scroll up a little bit. So I've got these two vectors, right? V is 1, 2, 5, U is -1, 0, 1. I want to calculate the projection of V onto U. Okay, so let's do that. So I'm going to do projection V onto U. So U is a little bit lower. I'm projecting V onto U, which I can also write as, it looks like that in our course notes. Okay, so when I go to do this, right, I'm going to be thinking about this formula here. So I'm going to say V dot U over U dot u multiplied by u. Okay, so this right here will be a scalar. This is a vector. When I do this, I'm going to get a vector output, okay, because I've got a scalar multiplying by what I'm projecting onto. Okay, so let's plug in what we have. This is going to look like v, 1, 2, 5, dot u, minus 1, 0, 1, all over u dot u, which is minus 1, 0, 1, dot minus 1, 0, 1, times my u, which is minus 1, 0, 1. Okay. So, right, I saw my projection formula, I wrote it down, and I'm going to plug in what I have because I'm doing v onto u. So I'm going to put those into the same spot. So let's go ahead and do our dot product. Remember, our dot product was, I'm going to multiply corresponding components together, and I'm going to add them up. So this is going to look like 1 times a minus 1, plus 2 times 0, plus 5 times 1, divided by, I'm going to do the dot product down here. So corresponding components, plus 0 times 0, plus 1 times 1. And that whole thing is multiplied by my components for u. Okay, so this is going to look like 1 times minus 1, that's a minus 1, plus 2 times 0, plus 5 times 1, all over 1 times minus 1, that's a positive 1, plus 0, plus a positive 1. Okay, so this is going to be minus 1 plus 5 is 4. 1 plus 1 is 2. Okay, so 4 divided by 2 is equal to 2. Okay, which now I can multiply this through. So I'm going to get the projection of v onto u is equal to minus 2, 0, whoops, sorry, positive 2. And that's our projection. Okay. We weren't asked for it, but let's go ahead and calculate out what's our orthogonal component projection. That's our Q. Right, so that was equal to V minus our projection. Okay, so my V was equal to, so V we were given at the very beginning. That's 1, 2, 5, minus the projection, minus 2, 0, 2. So that's component to component, 1 minus a minus 2, 2 minus 0, 5 minus 2. That's equal to 3, 2. Okay, so this is my orthogonal component. It was equal to, this was in green when we did our notes before. Okay. Now, right, these two should be orthogonal to each other, right? That's what we claimed before. We said that, so this is just our check. We said that the projection of V onto U should be orthogonal to our orthogonal component, right? So I can use my dot product to confirm that these two are orthogonal to each other. So use the dot product to show. If these two are orthogonal, the dot product should be equal to 0, right? So let's go ahead and try that. So I'm going to do my dot product here. So I'm going to use the projection. So minus 2, 0, 2, dot with my orthogonal, 3, 2, 3. So components to components. So minus 2 times 3 plus 0 times 2 plus 2 times 3. So this is minus 6 plus 0 plus a positive 6, which is going to equal to 0. My dot product is equal to 0. The angle between this one and this one is equal to 90 degrees. Okay. So that's how we show that those two are orthogonal to each other, which they should be because we calculated this one from our projection. Okay. So that's the application of the dot product. That's how we would actually use the dot product. And that's how you're actually going to be using the dot product a lot. We also use the dot product to show that two vectors are perpendicular to each other, that they're orthogonal. Okay. By taking the dot product and showing, just like we did here, that the dot product was equal to 0. Okay. So that's what I have for chapter 1.3. What I'd like to do for actually the rest of the class period is to work through classwork problems. Okay, if I work through classwork problems, I'm going to turn off the recording as I work through classwork problems, just so in case you guys have questions you want to ask me about it, then we can. And then, Amy, I encourage you to actually also ask about it. So I'm going to